Okay, so welcome back. So let's talk about radiocarbon dating a little bit more and talk about finding the age of some artifact or the age of a fossil or something that we found buried somewhere, okay? And again, first of all, radiocarbon dating only works with things that used to be alive, okay? Things that have carbon in them, right? Which is dead, things that used to be alive because we're carbon-based organisms. So our body is constantly producing carbon until we die, right? So when we die, our body has a certain number of a certain amount of carbon. So, but that carbon basically decays, right, into an isotope. So carbon-14 will decay to carbon-12, right? Because it's more stable. Okay. So in any case, we can figure out how long something has been dead. Okay, based on certain assumptions, right? There are a lot of assumptions that go into this, and there's lots of things that could affect this. So that's one of the cons to trusting radiocarbon dating is we don't know what was around the dead things. Was there a river there? That would definitely affect the amount of carbon in the organism and other things. But in any case, this is what we're going to do. So again, I'm going to use the formula that we did to show you, okay, if I have A equals A naught times e to the kt, right? And I want to solve for t. Well, in this case, well, first of all, since we're talking about radiocarbon dating, we know that K from the previous video is equal to the natural log of 1/2 divided by the half-life, which in this case is 5730. Okay, so we know that that's the constant K. And again, we know that this is approximately equal to negative 0.00012009 12094, I believe, but I'll leave it at 12.09. Okay. So now, but I'm going to leave this in here. Okay? So, this is for finding K. But if I solve for time, then what I end up getting is this, right? So if I solve this for time, I end up getting what? The natural log of A divided by A naught. So what is this? This is the proportion of the initial amount that I have left over. Okay, so this is a proportion. Okay, remember that. And so what do I get? I get natural log of this divided by the constant. And so this formula gives me the amount of time that has passed, okay, from the time that I had my initial amount. And it's the natural log of the proportion of the amounts, the current amount divided by the initial amount, divided by the decay constant, okay? Which in this case is this, approximately, okay? So if I wanted to get the approximate amount of time that something was dead for carbon-14, I would use this time along with this decay constant, okay? So let's do that. So in this example here, it says a bone fragment found that contains 20% of its original carbon-14. So I'm going to say that again. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? Okay, well, it says there's 20% of its original amount left, right? That's what it means when it says that is found to contain, that contains 20% of its original amount. This is the proportion of its original amount. So that means that this proportion is going to be 0.2, right? We don't use percentages, we use decimals. So it's going to be natural log of 0.2. Why? Because 20% of its original amount is telling us that A divided by A naught is equal to 0.2. And so now we're going to just divide by the constant, which is approximately negative 0.000129. Okay. Oh, 968, so this should be rounded. Yeah. This should be rounded to 10. Okay, so we can drop the 0, so yeah, it should be that. Okay. So now if I stick this in my calculator, how many years? Well, let's see, we get and we get approximately 13,301 years. And that's how old the bone fragment is, according to this information. Have a great day.